You can start.
Live streaming is on.
Ooh, look at that. So, well, you know that we have Jim Peebles talking to us today. And but first of all, I have a terrible confession to make, Jim. I never bought your book. The only copy I have is an illegal one I made on a photocopier many years ago in the Pleistocene when I was a student. But still, that book I still have around, and it's very nice for me that you are talking to us. And to the students, I'm going to say the usual thing, students and actually to everybody, don't be too polite. Just if you have a question, just go ahead and ask. If you don't ask questions, I will ask questions to Jim until you loosen up and understand that he's a human being like you and me.
Can anyone ask immediately when don't understand?
Yes. Yes. Okay. So, but if at all, I mean, if there are many questions, and you notice that somebody from Cuba is asking one, please give that person preference. Okay.
Good.
So,
Non-Cuba what? If non-Cuba?
I will explain that to you. So, go ahead, Jim, whenever you want.
So, hello to you in Cuba from here in New Jersey, where it is at last a bright sunny day. We've had a cool spring. So I intend to begin by showing you a series of images that illustrate the nature of our world around us as we look on increasingly large scales. This is, one may say, pre-science. It is images that you should be aware of if you are at all interested in cosmology or the large-scale nature of the universe. So I begin with this image, poor resolution by today's standard, but it was released in 1967, the first image of our planet Earth taken from far enough away that you can see that the Earth is round. Of course, it was perfectly clear then that the Earth is round, but knowing that from indirect evidence and seeing it are two different things. This image made a great impression on many people. An illustration of that is this publication, the Whole Earth Catalog. That's the same image. It is a thick volume of tools for carpentry, farming, home care, all hand tools, devices, as we would now put it, for sustainable living. The world is a finite, limited place, and we should be taking better care of it. This is the next planet out, planet Mars. It's a desert, but beautiful images taken by NASA satellites showing here what a classic delta of a river. At one time, Mars was very different. Here is the next planet out, planet Mercury, what am I saying? Jupiter. Its composition is very different from Mars or Earth, much closer to the composition of the sun, largely hydrogen and helium. The mass of this planet is too small to drive thermonuclear reactions that cause stars to form, but it still is radiating energy because it's cooling off from its heat of formation, cooling off by currents of warm gas that flow to the surface, then cool and sink. That radial motion is twisted by the rotation of the planet to make these marvelous patterns. A lesson I should have remembered to say from this is you look in different places, you tend to see new things. Our sun is a star. Here's a map of the nearby stars. You can see Sirius, the largest. The sizes of these stars are greatly exaggerated relative to their separations, but the relative sizes of the stars are realistic. So you see in the center the sun, you see to the right Sirius A, It is twice the mass of the sun. That extra mass causes extra pressure that causes thermonuclear reactions to release heat far more rapidly. Sirius A is 25 times the luminosity of the sun. The high luminosity goes with a high surface temperature. It's a bluish star, hot. Next to it, you see a small dot, that's Sirius B. Its mass is comparable to that of the sun, but is far more compact. It was started out even more massive than Sirius A. It consumed its nuclear fuel more rapidly. It contracted then to a white dwarf of carbon and oxygen. You see a few other stars that are larger than the sun, more massive, more luminous. You see several of similar size, and you see many more that are smaller than the sun, cooler surfaces, redder. An interesting star is down below, and I might explain these lines. If you start at the sun and move left until you reach this line coming out of the plane of the screen and down, you see Proxima Centauri, a very low mass star, but it has interest because it has two planets, and one a mass comparable to that of the Earth, and is just the right distance from the star that water on the surface of this planet would neither boil off nor freeze. Wouldn't you just love to see what's on the surface of this planet? It's 4 light years away, which means it's going to be a real heroic effort to get an observatory out there. But you can imagine people are already thinking how best to do that. The odds are most of these stars have planets. It's not easy to find them, but astronomers are making great progress at that. We are in a galaxy of stars. It's flattened like a disk. It's shaped very much like this, another galaxy of stars nearby. This disk of stars is seen very close to face on. You see elegant trails of dust, dark lanes, interstellar dust that is absorbing starlight. You see blue spots here and there. That's where stars have formed out of interstellar matter fairly recently. Those young stars will include massive ones that have more limited lifetimes, but while they're alive, are really bright and hot and blue. You see here and there red spots. That's where interstellar gas has been ionized by hot young stars. The plasma, the ionized hydrogen largely, when it recombines, gives emission lines. The one in the red, 6,600 angstroms, 660 microns, isn't it? It's red and a very prominent line, and you see them speckled around. You notice a blue glow near the center. The contrast doesn't show correctly the blue glow extending through this whole galaxy. That's the light of some 10,000 million stars similar to the sun. From the evidence in our nearby region in our galaxy, there are about as many planets around stars as there are stars. So it's a very good bet that in this galaxy there are some 10,000 million planets on which all sorts of wonderful things are happening that we can be very sure that the human race will never, ever see. After all, this is 10 million light years away. An illustration of the fact that there is much about the universe we will never know. We will catch glimpses, but we will always be shrouded in mystery. I should mention that in the center of this galaxy, if you look really closely, the upper left shows a Hubble Space Telescope snapshot of the very center of this galaxy. You see dust lanes running in a spiral pattern and approaching that bright spot in the center. That's a clump of stars, 1 million stars roughly. In our galaxy, there is a similar clump of stars, and at the center of it, there is a black hole, or at least a massive compact object with all of the features you'd expect of a black hole, with mass 4 times 10 to the 6, 4 million solar masses. Maybe inside this star cluster there is a black hole, it's a little hard to tell so far. There are other galaxies. Down below, you see 3 or 4 examples of large galaxies nearby. You saw M101. There are 2 more spirals illustrated. You can see where they are by looking at this map. There's one elliptical, looks like a ball of gas, except this elliptical apparently recently accreted a spiral and left a dust lane running across it. The luminous galaxies are the red dots. The plots are in what people know as supergalactic coordinates, chosen because you see in these 2 images, these images are perpendicular images. This, let us say, looking face on, this one on the right looking from the side, okay? So for example, the dot in the upper left in the left-hand image, which is this wimpy little galaxy KK246, that dot is over here on the right at the same level. Orthogonal views. What you notice is how, and the black dots are less luminous galaxies. Enormous numbers, and you notice, well, first, they prefer to lie on this flattened plane, and second, there's almost a third of the volume of this region out to 8 megaparsecs, or about 25 million light years, just dead empty, apart from this one wimpy galaxy. Galaxies really strongly cluster. But this map shows a still deeper view. This is a section of the sky that was originally 50 degrees from the pole in a circle. A map of 1 million nearest galaxies made by Donald Shane and his colleague Carl Wirtanen in the late 1950s. A heroic effort. They had photographic plates of the sky. They had traveling microscope, and they painfully scanned these plates and recorded each galaxy. They counted up 1 million galaxies. Can you remember? Well, consider we didn't have computers in the late 1950s. They had a stack of data sheets and nothing they could do with them. It was a great pleasure when we came across this old data to turn it into a map. And I showed Donald Shane the map and asked him, so does this look like what you were seeing? And he laughed and said, I was looking at this one galaxy at a time. You see dead center, a tight concentration of galaxies called the coma cluster of galaxies, because that's a part of the constellations it's in. It is a very rich cluster of galaxies. You could say that it is a galaxy of galaxies. But now you look around, and here and there you see other tight clumps. And what you see on the left and what you see on the right are quite similar. This is a profound remark. We've gone up in scale and seen new things as we look on ever larger scales. But here, we've stopped seeing anything new. This is a remarkable phenomenon. It tells us, it illustrates, and of course it has been tested far more detail, that on large scales, the universe is the same everywhere. That's important because we couldn't imagine making a theory of the evolution of the universe if the universe were different in different locations. We make a theory of the evolution of the universe because the universe is much the same everywhere. As one says, technically it's homogeneous. If you're a statistician, you say it's a stationary random process. Good, Nikos will be telling you a lot more about this, but let's carry on and come to the notion of the expanding universe. The figure on the left is a caricature of the Dutch astronomer Willem de Sitter, Professor Dr. Willem de Sitter. This is a cartoon lampooning an interview of Professor Dr. Willem de Sitter in a Dutch newspaper. You can read the date 1930. The idea of an expanding universe was new there, and Professor Dr. Willem de Sitter was explaining how it goes. So imagine now that you live on the surface of a balloon. You live on the surface, you have 2 dimensions of space in which to move, and you have 1 dimension of time. Don't ask what's inside the balloon or outside it. You live on the balloon, that's your world. You live in one of these galaxies that are sketched out kind of schematically. Now, the balloon is being blown up. I must caution you, you are not expanding, aside from the usual biological effects. Galaxies are not expanding, apart from the fact that they may accrete matter and grow a little denser. But the distance between galaxies is increasing. You notice you sit on any one of those galaxies and you look around and you see the other galaxies moving away from you. You might say, wow, the universe is expanding and it's expanding away from me. But of course, if you went to another galaxy, you would see the same thing. That's the homogeneity of the universe. Good, the universe is expanding. You might, if you think about it a minute, observe that an observer on one galaxy will see the other galaxies moving away, and that the further the galaxy is from you, the more rapidly it's moving away. The recession velocity is proportional to the distance. That's a simple relation that the Belgian astronomer Georges Lemaitre predicted in 1927. Is in effect that the American astronomer Edwin Hubble discovered independently in 1929. And this shows some data from 1929, lower left. I don't know whether if you were shown that graph, you'd be all that impressed. It looks kind of close to a scatter plot. But Hubble had excellent instincts. And they soon extended this plot. The recession velocity is plotted vertically in the central figure in kilometers per second, 4.5. That's 10%. That's 4.5. Wait. Yeah, 4.5. That's 3/10⁴ kilometers per second. The velocity of light is 5/10⁵. That's 10% of the speed of light. Wow, 1936. I give you some perspective. I was 1 year old then. Hubble, with his assistant Hubble, had observed galaxies so far away that they're moving away from us at the speed of light. The lower right image shows that it took the better part of a century. Well, let's say half a century. No, more than half a century to get the next factor of 10 down here. Anyway, this certainly looks like the signature of an expanding universe. But we have more. It is observed that the universe is filled with a sea of radiation at microwave wavelengths. That's wavelengths from millimeters to centimeters to tens and hundreds of centimeters. A sea of radiation coming at us almost equally from all directions, filling the universe smoothly. The intensity, the spectrum, intensity at each wavelength, measurements are shown here. The solid colored curve rising over the peak and moving to the right is not a theory, that is a measurement obtained by a Michelson interferometer.
Professor, excuse me.
Hello, yes.
Hello, I have a question for you.
Please.
Okay, what do you mean when you refer that the universe is in expansion? I mean, do you refer that the region where the space-time could exist are increasing, or do you refer the fact that the matter inside the universe is in expansion?
Yes, it is often said that space is expanding. I don't like that statement because, as I said, galaxies are not expanding. What is the case is that the galaxies are moving away from each other. The words you attach to that is space expanding. Well, it's not meaningful. The statement we can make that is meaningful is that the distance between galaxies is increasing. according to this pattern. Fair enough? Or shall we continue with that?
Okay, thank you, thank you.
If I can have a follow-up on this.
Okay.
I have heard as a counter argument that the spaces, we can only meaningfully measure the distance between galaxies as we see them because those are large enough that their changes are measurable to us.
Yes.
And that the size of the galaxy is actually expanding as well. We just are not able to detect it. Is that fair to say?
I do not think it's fair, although I am not familiar with precise enough measurements of sizes of. Oh, well, no, of course. Recall that galaxies at great distance can be observed. With modern telescopes, particularly the HST in space, one can look at the sizes of galaxies that are quite distant from us. These distant galaxies are seen as they were in the past because of the light travel time to get from there to here. These distant galaxies look younger. They have more young stars, but their sizes are about what you would expect if galaxies are not increasing in size. Of course, there is very good evidence that you and I are not expanding, apart from biological effects. And of course, surveyors have very precise measurements of the Earth. The Earth is not expanding. Shall I go on?
Yes, thank you.
I have a question on this as well. So,
okay.
Did I get this right? I always understood it that technically it is the space is expanding, but we just cannot measure it. Is this a take-home message? Or
I would not take home the message that space is expanding because I don't know what it means.
Okay, yeah, but just from the discussion we just had about that some stuff is not expanding, because I mean it might be a nitty-gritty detail, but conceptually it's different if stuff is not expanding or if stuff is expanding, but we cannot measure it, right?
Oh, right. But let us consider measuring it. Let us consider measuring, for example, the radius of the Earth, or measuring the distance between the Sun and the Earth. That distance is monitored with exquisite precision these days. It's not increasing.
Okay.
It is indeed confusing because to these statements, the reply I've heard, I also don't know what it means that the space is expanding. But I've heard the answer to this, or the reply, saying the point is that even the rulers that we would use for measuring are living in the same space-time, and therefore they would be proportionally changing. So we wouldn't be able to measure it in this way.
But we have, of course, lots of control on rulers. You have mechanical rulers made of materials. You have optical interferometers that measure lengths. That gives us a set of length standards that can measure your height as a function of time, measure the Earth-Moon distance as a function of time, and so on. This gives us a standard of lengths, and in that standard, the galaxy is not expanding, at least as far as we know, but the distance between galaxies is increasing.
Excuse me?
Please?
I have a question. I have curiosity. I would like to know what does make the space expand?
We do not know. We have a description that in mathematical terms, as you will hear from Nikos, treats the evolution of the universe that is expanding. We have ideas about what the universe was doing before it was expanding. We do not have a well-tested theory. That is to say, our theory is incomplete. We postulate that in the early stage that there was a time when the universe was dense and hot and rapidly expanding. From that, we draw conclusions, predictions that we can test. That part of the theory is very well tested. But you notice it starts with a postulate that the universe is expanding and cooling as time goes on. We do not know why those initial conditions are what they are. In that sense, the theory is incomplete. All theories are incomplete in a similar sense. All of our physics is incomplete. We just must live with that. Just as our knowledge of what's going on in that galaxy I showed you is very incomplete.
Okay. Do you think that this increasing of the space has an upper limit?
Oh, no.
I mean, there could be a moment that it's not necessary for the space to expand anymore. It's a curiosity that I have.
Yes, yes. And of course, if you pull an elastic band, you will break it. But that's not the case with the expanding universe. The expansion may stop in the future. That depends on what is happening to the cosmological constant, if I get around to talking about it. The universe, in the theory of the expanding universe based on Einstein's general theory of relativity, the universe could stop expanding in the future and collapse, or it could continue expanding into the indefinite future. The indication from what we know now, it's only an indication, is that the universe will keep expanding into the indefinite future. There will be a time then, very far from now, when the individual galaxies can't even see each other, they're so far apart. The stars in the galaxies will exhaust their supplies of nuclear fuel. There would be these dead remnants of stars that will slowly settle and eventually collapse to black holes. A dead, nearly empty universe could happen. I wouldn't worry about it because we know far more about what the universe used to be doing because it left fossils than we know about what the universe will be doing.
Thank you very much for your answer, Professor.
Sorry?
Sorry, can I just want to confirm that if I understand what you're saying properly.
Yes.
So basically what you're saying is that the galaxies are running away from each other. We don't know where, but that does not imply that the space is expanding. But what it implies is that the universe in itself is expanding, but not the space. And this is what the misunderstanding is generally when people talk about space expanding. What they actually should say is that things are running away from each other and we just don't know where they're going. But that wouldn't mean there's any expansion in space, right? This is
very good. The only thing I would change in your remarks is we don't know where.
Right.
But on the other hand, I'm not sure why I objected to that. They're moving apart. You might ask, where are they moving to? Well, remember this image. This is a closed universe. The evidence we have is that our universe is close to infinite, but never mind. If you sit on a galaxy and look around you, you see other galaxies, you see no edge to the universe. As this balloon expands, the distance between galaxies increases. You may ask, well, where are they going to? Well, they're going to other parts of the universe. The universe is everywhere. Remember, the theory that works very well is that the universe is the same everywhere on large scales. There is no elsewhere. The universe is everywhere, that we can see at least.
Thank you. Yeah, this is just what I wanted to confirm. Thank you.
I have a question.
Please go ahead.
Why will the universe work differently to a common galaxy?
Well, they both satisfy the same physics as far as we know. So a galaxy could expand if it does not have gravity that holds it together. a big difference between the gravity holding a galaxy together and the gravity that could be holding the universe together is that the galaxy is an isolated, compact thing. It has edges. So far as we know, the universe does not have edges. It's the same everywhere. So if the mass of the universe were substantially larger than we think it is, the universe would have been expanding, then slowing the expansion because of the attraction of gravity. But of course, slowing the expansion everywhere at about the same rate, apart from local irregularities in the mass density. In this hypothetical universe with a larger mass density, the universe would stop expanding and collapse. This would turn around to a big crunch. The difference, as I say, is that the universe is the same everywhere and a galaxy has edges. These are interesting questions. I'd be happy to keep going the rest of my time, but maybe we should go on to another. Yeah. This figure shows the spectrum of the radiation that is filling space. This radiation is everywhere. Of course, it hits the Earth, it gets absorbed, but most of space is empty and the universe is, this radiation is just freely moving about in all directions, almost the same intensity everywhere, just a sea of radiation filling space. It has a spectrum, which is to say an intensity at each wavelength, as above, or frequency as below. You see dots, there are measurements. You see a dotted line, perhaps, it's awfully faint. That's a theory. You see two solid curves near the top, colored blue and red. Those are measurements. You see that theory and measurements follow that dotted line very closely. So is this all clear so far? Good. The dotted line is a thermal spectrum. Thermodynamics tells us that if you place radiation in a container that has reflecting walls, perfectly reflecting, and let the radiation sit there a long time, it will relax to statistical equilibrium. The intensity will follow the intensity as a function of wavelength will follow that dotted curve. The space you see is filled with a sea of radiation that has relaxed to thermal statistical equilibrium. You're all familiar with an example of this. You stand by a fire, you feel the radiant heat. That radiation is close to thermal equilibrium, not exactly, but a good approximation. It has an intensity and wavelength. Please, go ahead.
What does it mean, CMB?
CMB is, where do you see CMB? Oh, up above, cosmic microwave background.
Okay, thank you.
That's a good question. And what does it mean? Phyras and Cobra. Cobra, bottom blue, is a Canadian experiment, a rocket flown from White Sands in New Mexico, US, that made one of the first two measurements of the intensity of this radiation over the peak. Phyras, far infrared astronomical, I don't know what FDS is, a US satellite measurement. It's a bit of history. You know, I'm Canadian, and so I take some pride in the fact that the Cobra measurement done by a team of 3 people almost beat the NASA Phyras program that had, well, a cast of a few dozen with many more engineers to help. The 2 experiments were in progress for over 15 years. They came to results independently within the space of a few months. The first to get on the air would receive great recognition. That was Cobra. A Nobel Prize for that great feat, well deserved. But Herb Gush, the leader of the other program, came in second. He got deep respect from colleagues who know what's going on, but no Nobel Prize. This is an aspect of life, which I always feel uneasy about, but well, what can you do? Anyway, this thermal spectrum has a temperature. Change the temperature, you'll change the predicted intensity at each wavelength. This temperature, 2.7325. Don't write it down. The temperature is measured to exquisite precision. It is exquisitely close to what you would get if the radiation filling space, this radiation is not starlight, you understand, that's at much shorter wavelengths. This sea of radiation has all the characteristics you would expect if it had relaxed to thermal equilibrium. Now that's deeply significant because the universe now is transparent at these wavelengths. There's nothing to cause radiation to relax to thermal equilibrium. This means, the best bet is, that this radiation was thermalized, this radiation was forced to relax to statistical equilibrium when the universe was dense and hot enough to be optically thick to absorb and radiate radiation many times to relax to thermal equilibrium. You get the point? The universe had to have been very different when this thermal spectrum was imposed on it. It had to have been dense and hot. This is, in other words, close to tangible evidence that the universe used to be very different from what it is now. I pause for questions. And forgive me for one moment, I should close the door.
Boris, this is your moment.
Okay.
Okay.
I have a question.
What?
I wanted to ask, what's necessary for a galaxy to be created? And how long does it take to a galaxy to exist? I mean millions of years? And do new galaxies born every day?
I didn't catch the last remark, but let me just begin by saying we have a pretty accurate measure of the time since the universe was very dense and hot. About 13 gigayears, 13,000 million years. The galaxies are almost that old. Our galaxy has stars approaching that age. Stellar evolution ages can be computed from the properties of the stars. How did the galaxies form? We have a theory. Parts of the theory are well tested, parts are not so well tested. That's just the way science is. You have firm results that you trust, and you have ideas that you're not so sure about. Ideas about how galaxies form, well, very simply, in the early universe, gravity is trying to slow the expansion of the universe. Gravity of matter is slowing the expansion of the universe. Any slight irregularity in the mass distribution in the early universe will grow more prominent because a denser region has stronger gravity that more rapidly slows the expansion. And so as a dense region's expansion slows, it will eventually stop expanding and collapse. And that concentration of matter will be a galaxy. That is a first approximation to what we think happened. Gravity caused matter to collapse into clumps. Gravity held the clumps at fixed size, but the distance between clumps is increasing. Fair enough?
Okay. And the other question was, do new galaxies born every day?
No.
No. Okay.
The galaxies around us all are old. The idea is that in the early universe, the density was very high, gravity was very strong, and it was causing the formation of these concentrations of matter, the galaxies. The universe now has quite a low mass density. Outside galaxies, the mass density is quite low. Gravity is not very strong, so gravity is no longer gathering matter to form young galaxies. A galaxy, a low mass galaxy tends to have a lot of interstellar gas still present. And so that gas is available to form young stars. You saw in the beautiful photograph of a nearby spiral galaxy, the blue regions, those are clusters of young stars. So in galaxies, stars are still forming. In low mass galaxies, star formation is relatively more common. But still, a low mass galaxy has old stars. So it is old, but still forming stars. I want some questions about this wonderful graph.
I do have actually a kind of a question which builds on what Oris just asked. So you say that these galaxies, well, so you have irregularities that are built up at the beginning and then they grow because gravity is attractive, etc. And we know that those irregularities were there in the first place because we have galaxies now.
Right.
Yeah. But
did you have a but or?
Yes, I was about to finish. So we see that we see galaxies now, and these are the proof that in the first place we had irregularities. So it was not a perfect process, right? A completely smooth, homogeneous process. But these irregularities, where did they come from in the first place?
Yes, it is a very good question. There are speculative answers, but not ones that you should trust too much. In the name of inflation, I don't want to get into that detail. I'm forced to repeat that we have a theory that is incomplete. We postulate a beginning. That beginning is a dense, hot, rapidly expanding universe with those small departures from exact uniformity that gravity will cause to collect into galaxies. We illustrate that by this image. You see how clumpy it is. Gravity has done this too. This is a very large scale. There's hundreds of thousands of galaxies in this plot. The irregularity due to gravity, gathering the galaxies together into clumps. That same process on a smaller scale began gathering matter into individual galaxies. Shall we go on? I want to have a question about this figure.
Yes, can I make a question about this graph?
Please.
What's the physical interpretation of this microwave spectrum?
The physical interpretation. This is radiation that has the features of radiation that has relaxed to thermal equilibrium. Let me say again, thermodynamics tells us if you place radiation into a box with walls that can absorb and emit radiation, but keep the energy of the radiation fixed. So you have this box, photons, bits of radiation are moving, hitting the wall, being re-radiated. The energy is shared in various ways among different photons. Let that sharing of energy go on a long time. You will reach a statistical equilibrium in which nothing much is changing. Some photons are promoted to higher energies, some demoted to lower energies. But the situation is stationary, it's in equilibrium. This equilibrium, sometimes called thermal equilibrium, allows you to predict the intensity of the radiation at each wavelength given just one number, the radiation temperature. This radiation has a temperature 2.725 degrees above absolute zero. That is the physical interpretation. It is radiation that looks like it is relaxed to statistical equilibrium. Then the step beyond that, why is this radiation the way it is? That can't have happened in the universe as it is now. We require the postulate that the universe at one time was much denser and hotter, so that absorption and emission of radiation could be happening often enough to force this energy and radiation to relax to this very characteristic thermal spectrum. In short, it's a fossil evidence that the universe was different in the past.
Okay, thank you.
Shall I go on?
I have a question.
Good.
How is that this thermal equilibrium survive up to now? I mean, why is it everywhere? Why it didn't change?
Yes, good. That's a very important point. Of course, it is changing because some of this radiation hits the Earth and is absorbed. So it is being interfered with. But the bodies like the sun and the Earth and the planets and the other planets are very rare compared to the amount of open space. So most of this radiation has never encountered any other object, which is to say, this spectrum has been affected by interaction with the matter in the universe, but the effect is tiny. In fact, observers are still looking for that effect. There would be small departures from exact thermal equilibrium. We're convinced the departures are there. They have not yet been seen.
And the expansion, it doesn't affect in any way.
Good for you. Very good question. What happens to this radiation as the universe expands? It was discovered early on that in the theory of the expanding universe, that based on Einstein's general theory of relativity, as the universe expands, the radiation temperature drops, but the spectrum remains thermal. That's just a wonderfully convenient property of the behavior of radiation in a uniformly expanding universe. Again, our universe is not uniformly expanding quite exactly because the mass distribution is not uniform. The remnant gravity of that mass distribution is causing small irregularities in the expansion rate. But that's a small effect, again, sought for but not yet found. So it is an aspect of it is a consequence of general relativity theory that as the universe expands, this radiation cools, but remains a thermal spectrum. That's important for another reason. Trace this expansion back in time, this radiation temperature was much larger. So I wasn't planning to talk about it, but one can go back in time to when this temperature was about 9 orders of magnitude larger, when the temperature was about 310 to the 9th Kelvin, which is about 1/10 of an MeV, which is high enough temperature that thermonuclear reactions can occur. Theory says that those thermonuclear reactions are going to leave most of the matter that is baryonic in hydrogen. It'll leave about 30% in helium, and there'll be trace amounts of lighter of the chemical elements. Another demonstration that the universe surely did expand from a very different state. You look around you and you find that the most abundant chemical element is hydrogen. Next most abundant at 30% by mass is helium, and very small amounts of the heavier elements.
Can I have a follow-up question on that?
Please.
So basically, that would mean that there will be a point in the future when we won't be able to see CMB at all.
Remember, it is everywhere, almost
Right.
exactly uniform.
But it will get cooler, right? So
yes, that is correct. And so eventually this will be so cool it can't be detected anymore. It will still be there, technically.
right.
But awfully cold.
And can we quantify how this, like the time scales here, or is it something which is because it's going to be based on the expansion and we do not understand the expansion, so will be difficult to put time scales on this?
Oh, well, no. I think we have a pretty good idea of timescales. First, of course, they are based on a theory. Einstein's general relativity theory describes the evolution of the universe. It describes how the temperature will vary with time. That is why we can take the present temperature around 3 Kelvin, and we can extrapolate back to the time when the age of the universe was about a minute, and discover that at that time the temperature was around 10 to the 9th Kelvin, and that thermonuclear reactions were taking place. We can extrapolate back less far into the past, a factor of 1,000 in expansion, when the temperature was about 3,000 Kelvin. That's when the radiation was just cool enough to allow hydrogen to exist as atomic hydrogen rather than thermally ionized as a plasma. So we have all of these timescales. The age of the universe when that happened is pretty reliably measured and tested against the predictions of the sort that I briefly will show you toward the end of this talk. But I think we're doing great to have all these questions instead. Shall I go on?
Yeah, thank you so much.
Here is a little piece of a little plastic plate, some water. I tapped the plate and then took a photograph with my cell phone. You see ripples. You see that they're more or less aligned with the edge of the plate. They're not perfect alignment. There are all kinds of irregularities, but there's a statistical pattern here. This is a crude illustration of the effect of boundary conditions on fluids. This gets kind of technical, but let's just think about this a while. The universe began very hot. When I use the word began, I mean we have postulated a time in the early universe when it was hot and dense and rapidly expanding. What happened before that? Well, that's not my department. We go forward in time from that postulated initial condition. We see that the temperature was so high that matter could not have existed in atomic state. It's thermally ionized, it's a plasma. The electrons in that plasma, the free electrons, scatter radiation very readily. The electrons are freely scattered by the ions, the atomic nuclei. The result is that matter and radiation act like a fluid that's slightly viscous. Now we have these departures from exact uniformity. Here is a measure of here one looks at a given Fourier component, a given plane wave, consider a plane wave. Its amplitude oscillates because of the pressure. It's an acoustic wave, just as I'm making noise, and that is causing the air to oscillate back and forth, a pressure wave. Here is a pressure wave in the distribution of the matter radiation fluid. It starts at 0 amplitude in the very early universe at the far left. It oscillates until you reach a temperature of 3,000 Kelvin, when the plasma abruptly combines to neutral atoms that don't interact with the radiation. The radiation is then free to grow in amplitude. You see it growing up. If I had chosen a slightly shorter wavelength, the decoupling, the time when the plasma disappeared, would leave that amplitude going negative, which is equivalent to positive, of course, headed downward. There has to be a wavelength in between when the amplitude is zero. Unlucky modes of oscillation. On the right, you see a prediction of what these modes of oscillations look like. K is wave number, 2 pi divided by wavelength. Amplitude, oscillations. Here on the bottom, the observed oscillations. You might notice timescales. This is 1970. So that's 52 years ago, 51. Well, who's counting? It's a half century ago. I never thought this would be observed. But it is. An interesting, big difference. You notice that these oscillations are there, but they have small amplitudes. Here they go to zero. Here they don't. Why is that? Well, that's because to fit all the data, we had to postulate non-baryonic dark matter. I think this is a hypothetical component. Okay, it's just I introduced it by hand because I'm desperate to fit the theory and the observations. We accept that the case for the existence of this dark matter is very good because with that postulate, we can fit a lot of measurements. You might be not overwhelmingly impressed by the measurements in the lower panel, but they're pretty good and they clearly show the effect of the dark matter. The dark matter does not act as part of the fluid. It doesn't interact with matter or radiation. So it doesn't care about these pressure waves. Since it is the dominant mass in matter, the pressure waves give only a small perturbation to the mean. The dark matter being unaffected by the acoustic oscillations, it is pretty direct evidence for this oscillation effect and the decoupling. Above, the bottom thing in the jargon is a power spectrum. It is the Fourier transform of the mass distribution, amplitude squared, absolute value squared. Same thing in the radiation above, except it's spherical harmonics. Let's just get back to the bottom line. The dots are measurements. The line is the theory. Spectacular fit. And it's spectacular that two different ways to look at the universe, the distribution of galaxies, the distribution of radiation. Well, the same theory fits both. It is measurements of this sort that give us confidence that we have about the right theory. I stress again, as I've said so many times, we don't have a complete theory. No theory is complete. We have a good approximation. I say that because it fits the measurements pretty well. In fact, in considerable detail. But it's only an approximation, that's for sure. Among other things, we don't know what this dark matter is. But I've talked on long enough about this, and I've used up an hour. Why don't we pause? Can I now eliminate this? Maybe by pressing Q? Amazing.
Yeah.
Can you see me now?
Not yet.
How do I
think
see?
you have to stop sharing your screen.
Well, I told it to stop sharing and it didn't obey.
You have to press the same share your screen button.
There you go.
Yes.
Am I with you? Can you see me? I see me.
Yes. Yes, we can see you now.
Where am I? Oh, okay.
In your office.
So I've used my aura.
No, but that's fine. I mean, we don't have a strict time limit, and I think people are enjoying this. So unless you, of course, want to stop. But why don't you keep on asking questions to Jim? Because, well...
You have been asking good questions, and I'd be glad to hear more.
So I have 2 questions.
Why can't I see you? Is there a way to make... Wait, before you go on, I want to see faces. How do I see faces?
Oh, okay. I've closed the camera to conserve bandwidth for the cubans. Let me open it.
So if you, yeah, there you go. That's Costas. This is my adoptive son, so to say.
Hello. So I have two questions. My first question is, you said before that we have evidence that the universe is flat and infinite. Flat I can understand, but how can we, on what grounds can we claim that the universe is infinite?
Very good, very good. Did I say the words infinite? I may have. If I did, it's an accident, thoughtlessness.
Nice.
We do not know what the universe is like at arbitrarily great distances from us. We can't observe that, so we can't know. It's just simply open.
So I was thinking maybe there was some kind of indirect proof, because my next question is related to this.
Okay.
Whether when we are talking about space, we assume implicitly that space has a certain topology, that it may or may not constrict its size. So I wanted to ask how measurable is topology, in the sense that I have found some articles explaining on how to extract, how to understand the topology from the cosmic microwave background radiation, but I haven't understood it yet. So I was kind of hoping that you could answer that.
Well, not very directly, but let us review. We live in a space-time, 3 spatial dimensions plus time. We can define surfaces of constant expansion time, roughly surfaces of constant density. These will be spatial surfaces. They will have a topology. It could be closed, as in a balloon, or open, a surface rather like a saddle, or these sections of constant time could be close to flat. With the normal geometry of Euclid, the evidence is, from the microwave background and other measurements, that space sections are close to flat.
Okay.
How is that inferred? It is from the details of I showed power spectra, these oscillations, that's functions of wavelength or spherical harmonic number that can be fitted to the observations. Among the parameters you fit are space curvature. And the answer comes back that the space curvature has to be very close to 0.
Okay.
You use general relativity theory to find the relation between observables, such as those oscillations, and the parameters that determine the evolution of the expanding of the universe. There are a handful of parameters: the baryon density, the dark matter density, and of course, space curvature. The parameters are constrained to fit the observations, and among the other constraints, space curvature very close to flat.
What about multiple connectedness?
Yes, perhaps you're thinking of a periodic universe.
I don't know. I'm not good enough for this. That's why I'm asking.
Well, let us consider a universe that is a cube, and that if you walk toward the edge of the cube, you reappear on the other side. Consider a torus. Consider a donut. Consider a bagel. All right. What is a good analogy? A bagel?
I think so, yes.
That's a familiar thing. So you sit on the surface of a donut or a bagel. You walk in one direction. You find that you walk around the circle of the bagel or donut. Go in the perpendicular direction, you'll follow a smaller distance before you get back to where you started because you've gone through the hole. That is a connected universe of a peculiar sort. It's possible to imagine that that's our universe. But if so, the smallest dimension has to be larger than anything we can see because we see no hints of the periodicity you'd expect of a donut-shaped donut topology that you might imagine for our universe. So our universe could have a donut topology. It could have some other effect. Our universe at great distance need not be anything like the universe we observe. All we can say is what we can observe looks very close to uniform with flat space sections.
Okay, thank you.
Sorry, can I add something, Jim?
Please.
Hi, this is Neil.
Hi, Neil.
Hi, how are you?
A familiar voice.
I'm back sitting in front of you, learning from you, as always.
I don't see your image.
Oh, I'll put that up if you insist.
I do.
Okay, good to see you.
You haven't changed.
Nor have you. Same office.
That's true. You see in the back the plant?
What's that? The plant is new.
20 years.
Yeah, right. Nothing's changed. So, yeah, Costas, just to answer your question a little more, if the universe were a torus, then, you know, there's only a finite volume in existence, in a sense. And if we imagine tracing out a sphere with us at the center, if we look out in all directions, and we try to construct this sphere, which is the surface of last scattering, where all these photons are emitted towards us, you know, that sphere will intersect this finite cube many, many times, because as Jim said, you can picture a periodic universe, and the sphere intersects the same, you know, the translated cube multiple times, and every time that it intersects, it's in a slightly different way. So in order to see that, what you should look for is correlations on the microwave sky, where essentially the same fluctuation would be seen from different angles and sliced through differently. And so there might be, you know, large correlations, but at very large angles on the sky. So one can search for these. People have done that. So far, there are no evidence for such correlations.
Right.
And so this seems to confirm that we live in, you know, the most trivial topology.
But Neil.
Yes.
Neil, this is Paul. This is actually something that Costas and I were discussing the other day.
Okay.
This is something about the topology, not the geometry force of the universe. So what about gravitational radiation? Because that allows you to go much, much, much farther away, right? What kind of you know, pattern or signature would you look for?
I think it would be similar. It would be large
Why?
angle. Well, okay, so two problems. One is with gravitational waves, you know, you need, in order to see this effect, you need some angular resolution. So you would need multiple gravitational wave detectors to basically focus on a given direction. And then you need to cross-correlate with other directions. But the other thing to say is the gravitational waves don't really go that much further. I mean, it's 14 billion years minus 300,000 or 400,000 to the surface of last scattering. You know, the gravitational waves go the extra 400,000 light years. There's not that much as compared to, we're already going most of the way to the singularity. So on large scales, you know, I mean, it's certainly very interesting to look for, but on large scales, we believe the gravitational waves, you know, on very large scales across the universe would be, wow, the very large scale, very large wavelength waves, you know, larger than the horizon last scattering, they would pretty much frozen, they wouldn't be evolving. But small scale ones, you know, might be. So Many ifs.
Because
Many ifs.
if, yes.
Small wavelength gravitational waves, which are oscillating, if we could detect big correlations at, points on the sky far apart, we might see that the initial singularity had some non-trivial topology.
I was not being that ambitious, but in any case, with the gravitational wave, the advantage is that you are catching the whole wave, right? While with electromagnetic radiation, you are looking at, you have to count photons, and that decays as 1 over r squared.
I think it's just the same.
Well, the strain is 1 over r.
I think it's just, they're both classical waves.
Yes, indeed.
Yes, but you have to measure energy, and you have to count photons, right? When you're looking at electromagnetic waves.
The regime these detectors operate in is one where there are many photons. They're not detecting individual photons. I mean, these are bolometers or... So, I mean, this is just radiation from a hot plasma. The detectors don't... I mean, most detectors, as far as I know, of the CMB, don't detect anything except the intensity. They don't have phase, typically don't have phase information.
Oh, well, no, they do these days. Remarkably, they're photon noise limited.
Okay.
In fact, these detectors are detecting the electric field as an oscillator.
So,
amazing stuff.
So that, in principle, that information can tell you that the photons really came off a thermal plasma.
Yes.
Do they have the sensitivity to see that?
Well,
I mean, if you look for the phase, if you correlate the phases and find the correlation decays, that should tell you the mean free path of the photons on the surface of Laplace scattering.
I don't know if that's, if you're thoroughly relaxed, you've lost memory of phases, right? They have to be...
Not in the unequal time correlation of the electric field. The equal time correlation is independent.
This is an interesting thought. People have startled me with how precisely this radiation can be measured, and maybe they can find such phase correlations. I just don't know.
Okay, I don't know either.
You know, I've just been reviewing thoughts on the origin of the black hole in the center of our galaxy. It's really quite peculiar. These black holes, one sees quasars, active galactic nuclei at high redshift. They have, apparently, the black hole that is the engine driving their high luminosity. Where in the world do those black holes come from? Was there a phase in the early universe when there could have been shocks forming here and there that formed these black holes? If they're not primeval, then how in the world did they form so early?
There are different theories about that, right? But Walter, they claim that there is an emerging consensus about that, but I have my doubts.
What is the claim? How? What is the claim?
So the claim, the general claim, which I have strong doubts about, is that there is an emerging consensus about the formation of these supermassive black holes.
I see.
Yeah.
Do you know what the consensus is?
It's not mine, first of all. Well, there are different ways of. Well, you either require a small or light, massive black holes to accrete the super-Eddington for very long, relatively, let's say, relatively long periods of time, or you postulated the existence of something. This was a very nice theory in the 60s, by which people invoked something called supermassive stars to explain quasars, which is what Jim was talking about before. But these are kind of supermassive gaseous clouds. We're talking about masses of 10 to the 4 and beyond. And then you can ask yourself, the question, how stable is that? It turns out that if you add rotation, different rotation, some relativistic corrections to it, and take into account turbulence, etc., they actually can survive for some time. And at some distance, at some appropriate, adequate distance, they collapse and form a more massive initial black hole, which will have enough time to accrete gas to become the kind of supermassive black holes that we observe nowadays. But these are just, theories thrown out there.
Is there a primordial seed for this structure?
Yes, of course. If there's also the third scenario in which you go to very, very large redshifts, and then you have very low metallicity stars, and these so-called, they are very fashionable these days. These population 3 stars can be very massive, right? They can have masses as large as 100 and beyond, and then they collapse and they form what they call seed black holes, and they might merge with each other. You might also ask yourself about the reckoning velocity, because this is going to, gravitational radiation is not it's going to give it some kind of initial kick velocity that might prevent that merge system to merge with another one, etc., etc. So a lot of too many free parameters for my taste, and it's not that clear how strong that consensus is.
I mentioned this simply because of the thought that if you're going to build these millions of solar mass and up to billions of solar mass, you're going to emit a lot of gravitational waves. And the question is, when does this happen? It has to be at higher redshift. Could it even be in the very early universe?
What is higher redshift for you?
The observed redshifts go up to, 8 or so? That's pretty far back in time.
Okay, then
modest affairs, and yet they are able to have these massive black holes.
Yes, in principle, you can measure these massive black holes masses of about 10 to the 14 to the 5 out of redshift of 20. But the point is that you don't have the information about redshift, right? When you measure the gravitational waves. The merger could be around the corner, or they could be at a redshift of 20. You don't know.
Oh, that is true, except they do have redshift information, don't they, through the theory of black hole formation.
Well, if you have the counterpart.
Theory, but I do hear reports of the redshift.
Yes, you hear a lot of things. You require an electromagnetic counterpart, but it's not that clear how easily you can do that and how easily you can associate that electromagnetic oscillation to the gravitational wave source, right?
One of the themes I was trying to imply in my talk was, it is startling that we can make progress that we believe is real because we can make theories that make predictions that match observations quite precisely. But at the same time, there are so many things we can observe only roughly, and many other things we cannot observe at all. One wonders, to what extent do these unobservable things affect our theories of what we can observe? It can't be too serious, I think, because otherwise we would not fit theory and observation. But there's got to be some effect. I have been spending my time recently trying to think of such things. Soon on the web you will see maybe the ravings of an aged lunatic. And possible things that are interesting and maybe just possibly observable.
Actually, in that sense, the first detection of gravitational waves was very disappointing because it was like a textbook detection.
Yes.
No surprise, nothing. It was disappointing in some sense.
You realize they had to choose such an example because they had to have a convincing detection.
Yeah.
a statistically detected signal would not be shown first.
That's true, but it was still amazing that such a textbook example came out just before they even went online.
Yes, that's right.
Yeah.
Well, they were not officially online, but officially the thing was working. The
Right.
was running.
Right. Just to come back to what Jim suggested about shockwaves in the early universe, just to say we have thought about this.
Mm.
And shockwaves are more or less inevitable, even with scale invariant, adiabatic perturbations of the minimal sort.
Mm-hmm.
Would form shockwaves. What we found is that the main damping mechanism for them is neutrino free streaming. That after the neutrinos decouple from the radiation, they of course travel freely through the plasma, and this damps away the perturbations on small scales, and in particular stops the formation of shock waves after some very early time, like 100th of a second.
Mm-hmm.
So yeah, that was somewhat disappointing. That there is a potential nonlinear mechanism in the very early universe. But we couldn't quite see how to use that mechanism to create, interesting nonlinear structures. The shocks themselves release gravitational waves, but we found that when two shocks collide, they can emit a gravitational wave, a sort of Cherenkov radiation of a gravitational wave. But it turns out the strain is about 10 orders of magnitude less than LIGO can detect, and so that's well beyond the current experiments. So who knows in the future?
Yeah.
Neil, would this include like effects of shock acceleration of particles as well?
We just did the most trivial possible thing, which is to solve the fluid equations for the photon, baryon, electron plasma, and show that linearized sound waves, do end up forming shocks. So didn't include more complex effects like magnetic fields and so on. And it's possible that there's something interesting there to be done.
Okay, because that would be interesting if you just imagine what we discussed yesterday with Andrew, that if you get a power law tail to the CMB from such processes, I don't know if that would be any option.
The power law tail in the spectrum, or?
Yes, for example, I don't know if there would be, if I don't know, if I'm thinking of the universe, which is like there are turbulent shocks moving around now, and if they are accelerating particles, you would have some cosmic ray background created by this process, which would imprint on the radiation. Maybe that's a bit speculative, everything now.
I think the stuff that happened in the very early universe is so early that thermalization is very efficient. So I think the trouble is thermal equilibrium is awfully robust. So I don't think
just to chip in, I guess you're talking about collisional shocks, Neil, are you?
I'm talking about primordial sound waves, the same thing Jim was discussing. They would have been traveling around in the early universe, and the mean free path of the photons is extremely small at early times, so it's a near perfect fluid.
Yeah.
As the wave travels along, it turns into a shock.
Yeah. So I guess that's different to what Mark's thinking, because Mark's thinking of a collisionless shock like we see in
yes.
Right, so that's why it's different. So you don't
exactly.
get. Can I ask a question, Neil, about the constraints of the magnetic field from present constraints of the magnetic fields in from early times. You know, see, remember the number of nanogauss fields are not preferred, or, you know, less than nanogauss fields. Has that changed at all since I last looked?
I'm sure Jim knows much better than me.
You know, I was just reviewing an old book, older probably than most of the people in this audience.
Yeah.
In which I talk about the formation of shocks in the fluid in the early universe. You did a much better job and more thorough job, of course. It's an example of effects that are fascinating and perhaps never will be observable.
Yes.
But of course, you keep looking for them because you might find some that are observable.
Absolutely.
So there is a tendency among in the cosmology community these days to focus on big projects that will repeat old measurements much better.
Right.
Euclid is a brilliant example of that. In the 1970s, I was working out the statistics of distributions in real space and redshift space, applying them to very modest data sets. The same program reappeared in the 90s with far better data sets and better analyses. Euclid will do it still better. They'll learn wonderful things, but it is kind of a narrow path through the universe, a narrow trend.
Right.
I got to think there are other directions to go that will give us new ways to look at this wonderfully complicated universe we live in, and maybe teach us more about the way it behaves.
Yes.
Can I ask a question about a comment that was made in the talk earlier? So you, maybe a picture. So you avoided the conclusion that the universe will be expanding faster and faster, and this way die out. And I was wondering if this is because you are not convinced by the current measurements of an acceleration or lambda, or because you keep an open mind about what dark energy really is. And
I think it's both. I think the evidence that the universe, the rate of expansion of the universe is increasing is pretty convincing. Remember, we never make proofs in natural science. We make persuasive cases. And the case for accelerated expansion is pretty direct and clear. You ask yourself, what will the future bring? Well, it depends, among other things, on whether the cosmological constant that's causing this rapid expansion is indeed constant or maybe is evolving. We don't know. There are ideas and theories, but they're not very tested. So, as I said earlier, and I'll repeat because it's so important, you can learn a lot more about the past because the past left fossil evidence. The future, well, it's about to happen, but it won't. You have no evidence. Inevitably, things are a lot more speculative. So I find it difficult to get excited about what will happen in the indefinite future than what has happened in the very remote but finite past. One should speculate about what will happen, but you shouldn't take it too seriously.
I have another question.
Oh.
Why, this cosmic radiation is telling us that at the beginning there was the Big Bang, and at the beginning there was this I don't know if everything was condensed in a point or in a region. Why did it happen? I mean, if everything was there and it was compact and everything, and we don't have any matter, why did it blow up?
Forgive me, I'm smiling because one of my bêtes noires What really annoys me is the phrase Big Bang. We use that phrase often, but it's totally misleading. Totally. A bang, wouldn't you agree, connotes an event in space-time, a position and a time. Something happened there, not anywhere else. That's not the theory of the expanding universe. The universe doesn't have an edge we can observe. There is no special place. No special place. The theory is of the evolution of the universe from a postulated initial condition. The theory is not about an event, a Big Bang. It's about an evolution from postulated initial conditions. Now, you might say, look, I'll extrapolate that postulated initial condition back in time. I'll end up at a singularity. Wow, what happened before that? Well, of course, we don't think that singularity is real, though it doesn't offend me because I don't know what to do about it. But the most popular view is inflation. Maybe, Neil, you have work on alternatives, and that's very important. And one might say that the singularity, if something interesting didn't happen, is a Big Bang of sorts, although it's a peculiar sort of Big Bang because it is a bang everywhere. I mean, well, I don't want to get into that singularity. What I do love so much is that we can postulate a start in the early universe and follow the implications forward in time and make a lot of measurements. So I gave you a long sermon, and because I was giggling, I maybe missed your question. You must not think that in the early universe, everything was piled up in a ball. That's quite wrong. This ball, this concentration, this clump, has an edge. The universe as we know it has no edge.
This is something that Kostas will talk about, actually. Yeah. Kostas, do you want to say something about this, Costa?
Only that I agree, because, yeah, I mean, well, it's pretty simple. If you assume that the universe is a point, I mean, this doesn't make sense. It's better to appeal to the singularity theorems as they have been formulated and just say that we have a finite past. Just that. Because otherwise you would making claims about something you cannot know.
Yes.
At least for the moment.
But Veronica, this is like what Leo was talking about. Do you remember when he was talking about the black hole interiors and that you cannot identify this singularity with a point? It's something that will happen. It's something that will happen in your future. It's not a place, but something that will happen at some point. So you can think of it but backwards.
But if I may add on that, because I think there is a fairness to when we think of it not as a point but as a reduced space, we are, at least me, as a person hearing, a physicist hearing from the outside, from a different field, it is said that we have evidence that everything was much denser at some point, and suddenly, in a relatively short span of time, it became much less dense. So this could have happened maybe while the universe was still large enough of infinite, and it turned from infinite to a slightly bigger. So I think we still don't. I think your point is that we don't have evidence that it was finite back then. Is that the point?
So, if the universe is infinite, it cannot be finite in the past.
No.
Right?
That's fair enough.
So the only statement that you can make is that there is no infinite. You cannot go back at time at infinity. You have a finite past. That's it. You cannot talk about having the universe in a finite space and then just exploding. This sounds more like a cartoon than actual science.
So Costas, sorry.
I have a question.
Sorry.
I have a question, sorry. I have two questions. The first one is, does space-time need matter to exist?
Can you repeat? Can you repeat the question, please?
Does space-time need matter to exist?
It's a philosophical question, isn't it?
No, not really. I mean, if it doesn't, why wasn't there a big compact moment and a space-time that has already existed?
Space-time, let us talk about the very early universe. Matter density is very high. Matter is everywhere, at least within the region we can now explore. It was there, everywhere, and moving apart, and expanding in the sense that the density is decreasing. That's the picture. How do you see this? Do you see a flaw in the logic of this picture?
I don't know. I will have to think about it, I guess.
That is a very good remark. Think about it. Send me an email.
Okay.
Maybe can I just elaborate the question, because I think it's a very good question. Why is the universe not empty? I mean,
I was asking that before.
You know, as far as we know, Minkowski space makes sense as a solution to the Einstein equations.
You are right.
It's a good solution, but it's not the right one.
It's worthless.
And there's some other solutions, quite a lot, in fact, which are also, you know, very nice, like de Sitter space-time, but they're wrong. So
They're wrong.
Why?
I suppose we must go into a version of the Anthropic Principle. You know, I've decided that there are two forms of the Anthropic Principle. A weak form was introduced by my teacher, Bob Dickey, at a time when cosmology was much more schematic than it is now. And he asked the question, how old is the universe? It wasn't well known then. Could the universe have been expanding only for 1 million years? The answer is absolutely not, because we require several billion years for stars to form the chemical elements. In a few generations of stars, we need those chemical elements. Then it requires maybe 500 million years to form the Earth, let it cool, life to form, intelligent life to arise, and look out and measure the expansion of the universe. If the universe is constructed in a logical way, not by miracles, then it's obvious that the universe has to have been expanding for several billion years. That's an anthropic argument of consistency of logic. Other anthropic arguments explain values of parameters by saying, well, there are lots of universes, and maybe we live in a universe that has the right set of physical parameters to allow life. I can't get very excited about that theory, although it is certainly widely discussed. Anyway, I would argue that the weak anthropic principle requires that we live in a universe that contains matter. It's not a very deep argument.
Right.
I guess you could say if there were an ensemble of universes, a multiverse, as people say, then we wouldn't expect to find ourselves in one of those universes that's dead empty. And Neil, I found it. You guys did a brilliant job with those nonlinear waves, but you know, there's nothing new in the world. And here, section 89 worked out a long, long time ago. When was this published? 1980.
Yes.
Where were you in 1980?
It's all in the Bible.
I know.
Costa, you wanted to ask something?
So the Anthropic Principle basically states, though, that the universe cannot be anything else than it already is.
Oh, well, I mean, did we need dark matter? I think the answer is no.
Well, what do you mean by need, in a sense?
I can imagine us flourishing in the universe without dark matter.
Of course.
And so our existence does not require dark matter. Our existence doesn't require mosquitoes. They're just there.
Are you sure about that?
Well,
that's very provoking.
This
I
is
know.
very, this is very, yeah. This is a slippery. This is a slippery slope.
We should get off it, I think. So Neil, what are you doing? Are you in Cuba?
No, I'm in Scotland.
Oh, okay.
Yeah.
Well,
I was lured to Cuba by Pau.
I see.
Yes.
Yes. I am luring people, yes, all the time.
Yes.
Can I just ask one question?
Oh, please.
So this question is mostly also for Neil, because
could you put your camera on?
Okay.
Yes,
Yeah, sure.
Yes.
Sure. Can you see me?
Yes.
Yes.
Hi.
Hi.
So actually, I was having a hard time wrapping my head around your question, where you said, what's the point of having any kind form of matter in space? So why do we have matter in space in the first place? But then I don't understand, what meaning does that space have in itself then? Because we are trying to, I don't know, maybe it's just a bit difficult for me to wrap my head around how is it helpful for me to understand a universe which has nothing. Maybe it's just a very naive question because I don't have any perspective.
No, it's not naive at all, and it's a question which Einstein struggled with. One of the things which guided him to his theory was Mach's principle, which is that roughly speaking, that large-scale distribution of matter or energy in the universe determines how things are locally, and so he more or less designed general relativity with this in mind, but then, as it turns out, general relativity doesn't require that at all, because it allows Minkowski space and other spaces like de Sitter space. And so I think it just remains a puzzle. Why is the universe full of matter? The easy way out is to say, well, we're made of matter, so there has to be some matter,
yes,
which is the Anthropic Principle. But and then you can start saying, well, we're older than some age, and therefore, the universe needed stars. But then you're starting to use the observations to, so that's just really looking at the answer. We would like some sort of principle which relates matter to geometry, and I think maybe there is one, but we're not there yet. A nice picture, just a metaphorical picture really, is that, what are particles? Well, particles themselves are geometrical. They are world lines in space-time. And having, objects of different dimension is certainly compatible with general relativity. You can have world lines, you can have strings, you can have sheets, you can have four-dimensional space-times. These are all geometrical structures. And then what is the relationship between them? how do you embed a lower dimensional object within a higher dimensional one? And essentially, this is what string theory is trying to do. So you could say string theory is, in fact, implementing Einstein's vision of geometry to describe what matter is. In string theory, there are objects of different dimension and they will interact and so on. It's a nice picture, but there's no evidence for it yet.
Very good.
So if we could cheat and instead of matter, let's weaken the question to just radiation. If say that you have an empty space and that you are accelerating, wouldn't this observer see thermal radiation? So couldn't radiation be or matter, let's say, be a matter of perspective of the observer? But then again, where does the observer find the way to accelerate? You can't have acceleration, an accelerating observer in an empty universe because it would use some kind of energy to accelerating. So maybe it's a bit cheating.
Right.
Well, you know, Einstein did worry, as was remarked, Neil, about Mach's principle. I think Ernst Mach would have said, the notion of acceleration in an otherwise empty universe is a nonsensical concept. Surely acceleration is meaningful only relative to what the rest of the universe is doing. Einstein liked this remark in the 1920s, and it led him to the notion of homogeneity. You see, we need to live in a galaxy in order to hold the debris of stellar evolution in order to make the heavy elements. We don't need all those other galaxies. What use are they to us?
Right.
Why do we live in a universe with all those other galaxies? The Machian idea is that, well, they're needed to make a complete universe. That's a vague remark, but best I can.
If I may continue on that idea, because I think anthropic principles are not very serious if we're trying to study physics, the world as independent of us, whether we live on it or not. And I think we could still make a theory of the world that contains everything that it does before, or even if we didn't exist. I mean, the world was real even if there were no intelligent beings to observe it, right? Dinosaurs, after all, were affected by things that happened before we existed, right? So in the same way, anything that is in the universe should be there, and the evidence is just that we happen now to be prepared to observe it, but that shouldn't be a requirement.
Of course, we have to exist. We have to have had a history. We should remark on one application of the anthropic principle that is really important. Recall the syllogism that vacuum, that the 0-point energy of material is real. If you don't take it into account, you get wrong energies. It's physically real. Energy, we know within well-tested physics, gravitates. So the gravitational mass, active or passive, of a material is affected by the quantum 0-point energies of the particles in it. The electromagnetic field in quantum physics is just another field. Its 0-point energies just as real, unless we have quantum mechanics wrong. The trouble is that those 0-point energies in the electromagnetic field add up to a ridiculously large energy density. Why in the world do we see such a small energy density, if it's present at all, in 0-point energy of the electromagnetic field? Well, there is the anthropic argument that in a multiverse in which the vacuum energy density has many different values for many different reasons, perhaps, we would live in a universe that has a modest vacuum energy density, small enough to allow the universe to have expanded for a couple of billion years and allow us to form. I know I've not been able to think of another application of the anthropic principle that grabs me at all. But the vacuum energy density of the quantum vacuum energy density is a really, really big puzzle. What other interpretations can there be?
I wouldn't be able to say. I don't really see the point of putting us in the center or in any path to understand physics in that large context. I also wonder about what I don't really understand those arguments when I hear them, trying to say that the observability of things should be in the way, and I think that might be a residual of the long time discussion in quantum mechanics regarding what it is that it really means, the entities that we talk about in quantum mechanics, and
yes, quantum mechanics has many subtle aspects, but consider molecular hydrogen, a hydrogen molecule. If you compute the binding energy, which is not difficult to do in good approximations, and forget to include the zero-point energy associated with the distance between the two hydrogen atoms, you get the wrong binding energy. It's not the observed value. To get the observed binding energy, you have to include the zero-point energy associated with the separation of the atoms. That's a real tangible effect. Nothing subtle about it. It's experimentally well checked. In quantum mechanics, the electromagnetic field is just a set of oscillators. It's just standard quantum mechanics. But yet we get the wrong answer. That is really disturbing.
That is in a way, but I would argue that our understanding of what is actually happening in an atom, whether what is the charge distribution inside the atom, once it's an atom and it's correlated, we cannot really anymore talk about positions or where the charge is or what is the exact description of the field and so on. We have managed to describe the transition between states that are stable states, and we have managed to calculate the energy or mass of those states with equations. But I think there is a distinction between when we talk about zero-point energy, that is already, I think, in the context of we not being able anymore to say the electrons is restricted to a specific position, the charge is concentrated there. What is the separation between the electrons field and the proton field, and how they, for all we know, they could be interchangeable, all these concepts. And therefore, zero-point energy seems to me like something else that we are not able to talk about given our description, a mathematical description.
Well, I wouldn't quite agree with that. We have a well-defined theory, Schrödinger's equation. We apply it to a molecule of hydrogen. We get a computed binding energy by well-described mathematics of the theory, and we compare it to measured binding energies, and we get consistency. You are thinking about what is actually going on inside that molecule. Quantum mechanics tells you not to do that. You are free to ignore that, of course. But quantum mechanics does give us an answer to the binding energy, if you include that h nu over 2 energy. And that's what I'm talking about.
So Jim, let me just object to that picture.
Okay.
Because when you talk about a binding energy, that's of course a difference between two energies. The
Oh,
energy
absolutely.
of the free particles and the bound object.
Yes.
That is not what you're talking about when you talk about vacuum energy. Vacuum energy is an absolute energy, not a difference from anything else. And to say that the metric, that the metric responds to the absolute vacuum energy, as computed in quantum field theory, is a big assumption.
I suppose so, but I'm doing it in a very simple-minded, very direct way.
Well, that may be what's wrong.
That may be what's wrong indeed, but show me how to get it right.
Well, Feynman had an idea. It didn't work out, but it was interesting that he proposed it, which is that he thought, I'm going to repeat what I read in an article by Frank Wilczek, where he summarized this Feynman proposal. Feynman never published it because it didn't work out.
Right.
But Feynman's view of fields was, and to paraphrase, that they weren't really fields. There are particles, there are photons. And a field is nothing but a representation of quantized photons. And each photon is following a world line, a null world line, etc. So if you start from the point of view that, if you like, Feynman diagrams are the real thing, they're particles in space-time, some of those diagrams are closed loops.
Mm-hmm.
The closed loops may have no legs externally.
Right.
And they represent the vacuum energy. And so he proposed that what we should do in calculating amplitudes is ignore the closed loops. Now, funnily enough, this doesn't quite work, because the closed loops, although they have no external legs, they do represent physical phenomena, which is that the real part is the vacuum energy, but the imaginary part is actually the particle production rate. So if you throw them out, you won't have particles being created in electric fields as they should be.
As observed.
Yes, as observed. So it's a tricky business, but it perhaps indicates that in some cleverer way of dealing with these closed loops, maybe you could avoid the problem you described.
Would the closed loops have legs to the gravitational field?
Yes, they would. So I'm talking about closed loops strictly, within the particle world. And then, of course, they all couple to gravity through external,
including the loops.
Exactly.
Right. So that
also suggests that, yes, how are you going to decouple them? Right.
Right. It's remarkable to me that Wolfgang Pauli in the 1930s understood this problem and wrote in a Handbuch der Physik article, we should ignore the zero-point modes of the electromagnetic field because obviously they're not real. Without any comment, let us sweep the zero-point modes of fields out under the carpet, but of course we'll keep them from particles.
Right.
But a particle, as you say, an electron is a field or a particle. The electromagnetic radiation is a field or a particle. You got to live with both sides.
Yes.
Of the coin. I promised Alison I'd be home by 1.
And I also would like that people listen to Nikos, because he has very interesting things to say, and he's a very smart person.
Nikos, I'm sorry. Are you there? We've taken all your time.
Yeah, no, don't worry. Take it. I might have time to finish my presentation by then. Don't worry.
No, it's good.
Very good. Okay, but
by the way, if I may make a short comment on this Anthropic Principle, it just reminds me of Weinberg's first chapter in the 3 first minutes that he speaks about this old Indian legend of how the universe began. To me, it sounds pretty much like that. I don't know about the weak version, but all we keep asking is what is before the other one and what was before that one. And philosophically, that doesn't make sense. Just
postponing.
Yeah, exactly.
Postponing an explanation.
Exactly. Thank you.
So, people, do you feel like this is a rhetoric question? But do you feel like listening to Nikos after say a 5 minutes break?
Of course.
Yes.
Yes.
I have a question.
Yes.
Okay. So let's come back at say 10 past.
Nikos, I'm very sorry I must miss your presentation, but I must go home.
Okay. So to continue with what we were discussing, we have now one of the smartest, most handsome and wonderful people I know, who is Nikos. And Nikos, by the way, you already have one question from Francisco.
Okay.
Yeah, can you hear me?
Yeah, I can hear you.
So, I have a question that is, can we predict what happened in the first moment of the universe with our actual understanding of the physics?
Okay. The first moment, like the first instance, probably not. I mean, the funny thing is we don't even know when that and if this first moment actually happened. And what I mean by that, actually the life of the universe, first of all, is very, very model dependent. It's if you say that my universe is not following the standard model that we believe it follows today, so that it is flat, it's homogeneous, it's isotropic, it has perfect fluid to interpret matter, etc., etc. If you say that one of this is dropped, then immediately you don't have the same life time for the universe. So it might be older or younger. And that's just one aspect of it. There's another even more awful, that in fact, well, if you restrict yourself to standard theory, which is GR, like Einstein's theory, then the first moment is actually a moment that you cannot approach. It's something that that your theory breaks. It's just like the singularity in a black hole, and that means that you have no way within this theory to approach this first moment. And what happens then is that all you can say about the first moment is pretty much theology. And the safest way to proceed in that case would be probably to change your theory of gravity and try something different. And in that case, if that point is no longer a singularity, this first moment is no longer a singularity, then yes, you could say something about it, but I don't think you can say something about it in general relativity and in the standard model we have. And I think Jim Peebles said something that he doesn't like, the expression Big Bang, which was it was coined as an irony towards the standard model. People have the idea that the universe somehow began, and that's not necessary. Okay, we have no direct indication that the universe began, and in that saying that space, time, and matter, that the universe consists of have some point of beginning, some moment of beginning. And from that perspective, it's not just an open question, it's a question that leads us to abandon standard theoretical lines, and as long as you abandon standard theoretical lines, you can say pretty much anything you want. I don't know if that answers the question.
Yeah, well, I wanted to ask that before, because when I think about a great quantity of matter in a small place, the idea of a black hole just pops in my head. And
And that's a wonderful difference between. Yeah, go on.
No, I just want to say that that's why I asked the question before.
If you remember these diagrams, I think Michalis Dafermo showed some of them of a Schwarzschild black hole that all observers somehow end up in the area within the black hole. So you have the horizon and there's a singularity on the top. Okay, so all observers will end up to that singularity and their timelines will stop there. Okay, the universe that we use today, the solution of GR that we're using to model the universe today, which is the Friedmann-Robertson-Walker, is exactly the same. It's just reversed. So you begin from such a singularity, so you cannot extend your timelines all the way to the future to some, all the way to the past to some past infinity. They begin from some impossible point, let's say in the future, in the past, and you are bound to end up in the future infinity, which is nothing but the Hubble horizon. And from that perspective, one has to make a small, let's say, discrimination. These are solutions that are mathematically possible solutions of general relativity. And speaking for Schwarzschild black hole or for black hole solutions in general, they're vacuum. There's no matter in there. It's one more of these examples that Neil was speaking about, that you have a lot of solutions in GR that are physically impossible. A black hole is modeled in general relativity as vacuum. Astrophysically or physically in general, that wouldn't be possible because we have an idea that stars collapse or some matter anyway collapses and creates this area where you cannot can no longer interfere with its exterior, so it forms some kind of horizon, some kind of event horizon. So the astrophysical black hole with the mathematical black hole, they look very much from the outside. So for an observer that lies outside a Schwarzschild black hole, he can tell no difference if he stands in the way he stands outside some other solution in some other theory of gravity, let's say, where you have an horizon and something else inside it. So no longer a singularity, but some extremely compacted matter. In general relativity, that's not possible. In other theories of gravity, that might be possible. The observer from the outside can tell no difference from that. In the universe, it's quite opposite. Is it someone?
Yes, I was about to say that I hate it when people say astrophysical and mathematical black holes. Keep on talking. Sorry.
Okay. I just wanted to say that it's the solutions that we have for black holes, which you can call mathematical black holes if you don't like that. Okay, are not necessarily what happens in nature. Right. So, yeah, from the perspective of general relativity, it's not that some star collapsed and gave you this. It's a bit tricky to think of that. So, extremely compacted matter that has collapsed from something doesn't mean a black hole. In the universe, because we're trying to speak cosmology, it's a bit different because you have matter inside. You know you have matter. You see this matter, and so your solution actually it's very hard to imagine what this matter what happens to this matter all the way back to the past, to that initial singularity, if that initial singularity actually exists, how this matter was compressed or whatever. So people tend to say that a theory has a problem and it breaks down all the way to the past, to that first moment.
So, Nikos, following on this, how should we take into account that thinking in the past as a big bang, as everything collapsed to a point and then expanded? This is very common. I've seen in many places, not just for general audience. To correct this view, how would you recommend to think about this that is more in line, more proper with what we really know and what really we can really say from studying this?
Well, the a way to think about it is that if the universe is infinite, which is not also necessary, but if the universe is infinite, it cannot go to a point. So what happens is that this infinite universe probably shrinks and shrinks and shrinks, or rather, the distance between different observers shrinks, and they're brought closer to each other. But that doesn't mean that eventually this space will become a point. I think the best version of the story I have heard, but it's just a story. I don't know if it's really solid mathematics behind it, is that space and time and matter all existed in some different form, in some form that is not described by general relativity. And this Big Bang, this first moment, is a kind of phase transition. And it's a point from which general relativity becomes a good approximation of the actual theory, if you want. So you can go till there, but you cannot go back because before that, because this theory breaks down. So the universe might have existed in a different state from what you know, what we understand today, in a different description from a theoretical standpoint, but you cannot have access to it with these tools. And that's a problem.
Okay, and following from that, right? So we cannot know what triggered that transition, that phase transition, or all we can say is what happened right after that transition happened. Correct?
Yeah, exactly. With from this theory, okay. There are several, let's say, versions of the theories, or even models within this theory, a bit trickier, like you can somehow rescale your space-time and make it look smaller, but it's still big enough to have a universe inside it. And this rescaling, this rescaling is the phase transition, and to have this rescaling, you might have some kind of a full evaporation of the universe, or a thermal death of the universe, of the previous universe, let's say. And in that case, this phase transition would allow you to get to this space-time and have this the solution that we work with. One could say that I think this was proposed by Penrose, and what he says that the universe would eventually someday die out. Okay, all black holes would be evaporated through Hawking radiation. All stars will probably collapse into neutron stars or black holes, and those will too evaporate, etc. And in some deep future, you will end up to have a universe of mere radiation and nothing else, no matter in it. And that universe suddenly comes to this point. So this phase transition could be that point, at the point that you have only radiation and nothing else in the universe. For that universe, the observers, how was it actually said? that for the observers of such a universe would see no difference from a sudden rescaling. And that rescaling could make the universe look suddenly a lot wider, so you could interpret it like a Big Bang. Okay. And I think that's the soundest way in general relativity to have a universe before our universe, and one afterwards, etc. Otherwise, you have to think different theories, and then what actually happened before or what will happen after depends highly on what additional terms you have added to your theory. So it's pretty much.
What do you think about this conformal cyclic cosmology, Nico?
Yeah, that's the idea.
Yes, before you answer that, can you make maybe a short summary for those of us actually who do not understand what the conformal cyclic cosmology is?
Or don't know what conformal cyclic cosmology is.
I'm not exactly sure if I can do that, but I will try. So the idea is that if you have this the space-time given by as I've told you, the universe, the way we describe the universe, the standard cosmological model, also known as lambda CDM FLRW, is a very specific solution of general relativity. It assumes that the universe is homogeneous, is isotropic, and that means that towards all directions you will see the same things. Matter is distributed homogeneously around you, and it also means that that your matter is dust, which accounts for standard and for dark matter, and either some bizarre fluid or some cosmological constant that accounts for this dark energy that you don't know what it is. And from a point of GR, this is a space-time. This is, you have how should I say this? It's a space-time, and the first thing you have to do on this is to measure distances, so you have some kind of metric. And the idea is that you can always rescale this metric and make this universe seem smaller or larger. And there are ways to do this that will not affect your, let's say, your theory. And this rescaling is called conformal transformation. So Penrose tried to say that I will find the physics that would make such a conformal transformation a possibility. Because mathematically, a conformal transformation is something you can always do, but it doesn't mean that that it's triggered physically and it will lead you to something equally physical from what you began. You might end up to something completely unphysical. So Penrose said, I will find a physical way to do it so that I will end up to something physical again. And the idea is that as the universe expands after the so-called Big Bang, it becomes colder, it becomes much thinner, let's say, not thinner, let's denser. And also physical processes lead all matter structures to somehow die. And that means that no new stars will be born as the universe becomes colder and colder, and the old ones will die. And as all these will die, you'd come to what we call a thermal death. And at the same time, all the remnants of these stars, like black holes, will also, Penrose assumes, will be evaporated by a process known as Hawking radiation. And that is how black holes can, let's say, emit particles. And these particles, as they are emitted, the mass of the black hole shrinks. So there is a theoretical possibility that after many, many millions of years, no new stars will be born, no new processes will happen, physical processes, And the only process that will be happening until no other black hole is left is this Hawking radiation. So in the end, you'll have a universe that has no matter in the standard way, no luminous or dark matter, no stars, no planets, no clouds, no nothing. It will only have this particles emitted from the black holes, this radiation. And that universe could, that situation could, for Penrose, interpret this phase transition that would allow him to mathematically enlarge his space-time, to make this rescaling, this conformal transformation. And so long as this conformal transformation is made possible physically, he suggests that you can go, it's not so hard, you can go to a new universe which is identical to the one you had, but for the observers that have, let's say, survived, for these particles that have survived from the old one, which is nothing but Hawking radiation, the new universe will appear to be growing from a very small state, which is, again, it's like going back, and this one is, again, very hot and very dense and allows for new processes to happen and new stars to be born, etc. I'm not sure if it's a very good explanation.
Nikos, I have a question.
Wait, 1 second. Wait, okay. Mark. Sorry, just one remark. So the one interesting thing about this theory is that he predicts that only massless particles could transit
will survive, exactly.
On to the next one. And he, in his theory, has this prediction that you should expect concentric cycles of peak events, like, for instance, supermassive black holes merging and emitting gravitational radiation. And they should be concentric, right? Because this is like having a boom being transported from universe into universe. And there were some claims of detection of these concentric cycles. But anyway.
I think they were disregarded at some point.
Yes,
what do you mean by these concentric circles? What are you observing here?
You could see the if I'm I don't know that, but I think you would see imprints of these gravitational waves on CMB.
That's right.
Yeah, which I think they believed when Penrose suggested that they had found them, and it appears that they haven't. Actually, it was something completely different.
Okay, maybe what I just wanted to ask is like about the time scales, because the Hawking radiation time scale is like 10 to the 60 years, if I remember.
Yeah. Depending on the mass of the initial mass of a black hole, but yes, it's very large.
So this would be like several e-folds of the timescale of the existing universe that we are talking about here.
Yeah. And it's even greater because all okay, not that greater, but you have to first, all of your standard matters, all of your stars, clouds, etc., should end up in black holes, and then these black holes should start emitting these particles and follow this process, which makes it a very huge timescale indeed.
Yes.
So anything else on that?
Professor, you say there's phase transformation in universe.
This phase transition, yes. If I think I missed the beginning.
What?
So what is your question? Can you answer question slowly, please?
I just don't know about that phase transition.
So could you define, Nico, what is a phase transition for him?
Imagine that you're the best analog I can think of is from thermodynamics. So you have ice and it turns to water, and that's a phase transition because the physical properties of what you had changed. In the same manner, I'm not probably using the right word when I say phase transition, but it's a word that is usually used. What they mean is that your physical universe, let's say the matter that you had, somehow changes. It has not that it does no longer has the same properties, but suddenly it passes from one state to another. And if we go on with Penrose's idea, for example, in the end of a previous eon, you will have only massless particles, only this radiation. But in the beginning of the new universe, you suddenly should have a very compressed, very hot, very dense fluid that would allow you to create electrons, protons, neutrons, and then atoms and molecules, etc. So this is a phase transition, how this very dispersed cloud of massless particles will end up to be a very compressed, hot, and dense cloud of massive particles that will give rise to the new universe, the new material universe. So that could be seen as a phase transition. It's matter that... Yeah, please.
Okay, so from hot fluid to something colder and then...
Yeah, exactly. That's one way you could see it. You could talk about it. Another one is that suddenly distances in space will be different for the old observers coming out of this massless particles coming out of the previous eon and entering the new one. So space also is passing.
What distance?
The distance between one particle and another. In the old eon, they should be large enough, very, very large, because the universe has expanded as much as possible. Suddenly, these distances will bring all these massless particles very, very close. And that's another transition you could call phase transition, for example. That's the rescaling of your spatial dimensions, if you want.
So the distance between particle and dark matter.
Costa. Oh, sorry.
Okay. So I have two questions. Actually, one question, which is two-parted. So the first question is that, from what I understand, this model is complete. It's time-like and light-like complete, right? It has infinite past and infinite future, right?
I guess so. Yes, I guess so.
Okay, so since you don't have these kinds of singularities, should we suspect that we need some kind of other fields to drive this physical process? I would imagine a scalar field, because the conformal transformation.
That sounds very, very, very correct, and I cannot think of something better, because usually conformal transformation leaves you such a scalar field as a byproduct. That's true, and also because you enter the universe, the new universe, in a very early stage, and that stage is usually the inflationary stage, let's say. Yes,
that was exactly my point.
To inflation, you'd need some scalar field, at least one scalar field, in fact.
So this model could be thought of as inflation plus, or something like that.
Before.
Yeah. Okay, so you basically need an unobservable scalar field, which necessitates this cyclic cosmology, and which also violates the energy conditions. Doesn't that seem a little bit unphysical? I mean, okay, why should we suppose that this thing exists?
Costa, back up, step by step. because this is becoming a dialogue, and I want everybody to follow. So elaborate on what you just said, and please ask the question.
So
Maybe you
does
can
any
explain what is conformal transformation in the first place, because there would be people who don't know that.
Yeah, maybe Nico should do it because it's your presentation, man.
Yeah. Yeah, I hoped I wouldn't need to go there. As I've told you, I will try to explain this mathematically, and that's not probably the best idea. What you have when you work with general relativity is just you need a metric so that you can measure distances, volumes, surfaces, whatever else, and curvature. So how this space-time that you're on is curved, twisted, or whatever. So you can imagine the metric, if you have no idea about differential geometry, you can imagine the metrics as let's say a matrix, n times n matrix, where n is your dimension, so it would be 4 in our case. And each element of this matrix tells you how you would measure, how would you combine dxi and dxj. So let's say the dx being your length on one direction, dxi on one direction, dxj on the other direction. How would all this be combined to give you the distance between 2 points? So in the Euclidean space, it just be an identity matrix. Okay, just ones in the diagonal and unity and zeros everywhere else. And your distance between 2 points would just be dx squared plus dy squared plus dz squared minus dt squared, because time goes with a minus there. In more complex, more curved, more whatever else you want space-times, this is no longer an identity matrix. It can be, first of all, the zeros need no longer be zeros, so you might have cross terms like dx with dy, etc. But it also could be depending on your coordinates, whatever. So conformal transformation is taking this matrix and let's say multiplied with a factor or an exponential of some function f, let's say, and this leads you to a new space. Let's say it's no new, which is a transformation of the old one. So the new metric is this exponential of f times the old one. And when you do that, there are some, your curvature changes as well, but some elements of your curvature remain the same. So what was Kostas referring to?
Excuse me, you were talking about the metric tensor and curvature.
Mm-hmm.
How are they related?
Yeah, generally you can say that the curvature is the second derivative, or rather a combination of the second derivatives of the metric. It's not as simple as that, because you can define curvature without metric, but if you have a metric, then you can always get the curvature by the second derivatives of the metric. So for a flat space-time that we have this identity matrix, this will be 0. For a space-time where the elements of the metric tensor are depending on the coordinates, they will have derivatives, and these derivatives will give you your curvature. And there are, let's say, elements, components of this curvature, of the curvature tensors, that are not affected by such a transformation. So while your metric expands or shrinks depending on what this exponential, this f function is doing, whether it shrinks or it enlarges or it rotates or whatever, your space-time, there are components of your curvature that will remain unaffected. And that's why it's because these components are called conformal, that's why you call this conformal transformation. And what Kostas was referring to is that whenever you make such a transformation, your new curvature, the part that is affected, carries on some scalar field in comparison to the previous one. So you can start from a space-time that is a solution of general relativity, make this transformation and go to a new space-time, which is also, let's say, a solution of general relativity, plus some scalar field. And this scalar field is usually considered to be very, very convenient because it can be the cosmological constant that gives this accelerating expansion to the universe. It can be one of the means to start inflation in the very early universe, and it can be whatever you can think of in that case. So it's very, very convenient, to go back to what Kostas said, to say that I will transform my space-time in such a manner that it will give me, again, my curvature, again, show my gravity, because curvature is gravity, plus some scalar field that will initiate inflation again and will take me to this new early universe when the older one is dying. I don't know if that pretty much covers it.
Can you? Yes.
Maybe I could help Nikos out a bit in explaining basically what the conformal transformation is. So go very simple to the basics. Take, for example, the plane, okay, and take a vector on that plane. So when you apply transformation of that vector, you have what happens is a combination of two things. The first is you have a dilation, where the length of the vector is gets bigger, changes. It either gets bigger or it gets smaller. And rotation. It rotates around an axis perpendicular to the plane. So a conformal transformation in geometry basically conserves the angles. So the only thing that remains is basically in plane geometry, a conformal transformation, what will do, it will just change the angle by a factor, a scalar factor. So if you take this to Riemannian geometry, conformal transformations, the preservation of angles essentially means that a conformal transformation is a transformation that preserves causal relations. Okay, so such a transformation, what will have as an effect is just a scalar lengthening of the proper time.
Costa.
Yes.
You should explain. You should explain why the preservation of angles is important in relativity. So that
I just did the angles in general relativity.
Just why? But the why is not. It might be trivial, and I understand why, but it might not be trivial for other people. So
why does it?
Yes, preserve causality.
I don't understand the question.
So why are angles important in this context?
Because angles arrive from the Riemann. Angles give you the Riemann tensor practically. That's what Pau probably refers to. That when you transpose a vector on a curved space-time, when it goes back, it will not meet itself, but will be some angle in there between its original.
I think you can go even simpler. Once you go to the Minkowski space, preservation of angles means preservation of the light cone. This
Yes,
is
that's
basically what the,
okay, yeah,
the
you're right,
metric
you're right.
tensor
That's
is.
that's the key word. If you go beyond 45 degrees, then you have a problem, right?
Yes.
Yeah, exactly.
So, so when you hear preservation of angles, it means preservation of. So what you get is just a scalar, a conformal transformation. What we'll do is that it's just scale the metric tensor by a scale, by a scalar. There is no
this
special language.
exponential thing, yes.
Yes.
Exactly. Yes.
So there is no. So that's why you need basically. That's why I asked earlier whether there is a scalar field coupled.
Yeah,
to
there's always a scalar field. But what I thought about it is that you can get your field equations after the transformation, and they will be similar to the older one plus this scalar field. So this scalar field can be interpreted as a new form of matter, which is true.
Can you remind me of the logic? I'm a bit.
Lost.
I understand that this
Can I make a comment? I think that you are confusing two things. So the conformal transformations preserve angles, normal angles. I mean, like you have two vectors that have a norm, like two normal vectors like in Euclidean space, and you compute the angle between these two vectors with a metric, and then you also compute the same angle with a metric that is conformally related to the previous one. Then the angle is the same. This is one thing. Another thing is the preservation of the light cones, and this is because conformal transformations preserve the null geodesics. So these are two different things, but both of them are preserved by conformal transformation.
So space-like and time-like lines are not conserved, but null lines are preserved.
Right. Right.
Okay, maybe what I wanted to ask is, I understand that these transformation have nice properties, but I'm just missing the context. Like, what does it mean what does this transformation mean? Like, do we require a symmetry, or how are they important? Like, I guess there's no God sitting somewhere and performing these transformations to our metric in the world. So
performing this transformation is something that's very, very usual. It just rescales your metric. It just rescales. How Kostas put it practically is right. It can help you rotate your vectors or make them larger or smaller. The fact is that it preserves angles.
So in the end,
so you can do it. You can do it anyway. There's no problem doing such a conformal transformation in anything. The point is that Penrose gave us, first of all, that you start from a physical space-time and end up to another physical space-time, which is not always the case when you perform this transformation, and also gave us a physical reason for this to happen, which is this whole idea about massless particles, which is the only thing left in the universe in the end.
So we're basically talking about a coordinate transformation, which doesn't change the physics, but my description of it.
In general, I think the conformal transformations can change the physics. You can start from a physical frame and end up to a non-physical frame. In this case, it doesn't change the physics. It only adds the scalar field, which is very well interpretable. So you're okay.
I just don't get, like, how is the scalar field popping up? So I'm thinking of the
it's this factor you multiply the metric with. It's this factor you multiply the metric with.
So how can I have one description without a particle and another one where the particle comes in? I mean, this is two physically different worlds.
Yeah, and the only way to connect them would be by saying, I think that when all you have in the universe is just radiation, massless particles, then what happens is that it makes no difference to your observers how small or how large is the universe. I think, Carlos, you have said that quite better than I do right now. And
well, no, what happens is that you only have radiation. Radiation is also is the only equation of state that also is invariant in the conformal transformation. Yeah, I don't know the details about the Penrose model. I have some doubts. I know the basics, and basically the problem is in this matching that you do between essentially the future of one universe. I think called ions or something like this, to the let's say the past of the next universe, because then you need to in order to do this matching of space times. You need to introduce this conformal factor in order to make things consistent, I think. But I don't know the details. I haven't looked too much at it.
I think it would be answered if you remember along with space, we also rescale time in that perspective. So for these observers, time doesn't have the same meaning with observers.
The idea precisely is that when one of the eras ends, there is no time, because basically
thank you. That's the key.
To have time, you need massive particles, and if everything has already decayed, either by Hawking radiation,
there is no time. So you're allowed to do this. Let's say
exactly. In the end, you only have radiation, so there is you don't have a reference of time.
Exactly. Thank you.
So did I get the conformal transformation stuff right by just saying that we just use a metric to describe our world, and we can perform a conformal transformation on it, and we would get a different metric which still describes our world but has an additional, like, it's not like
you have two metrics. You have two metrics. You have the metric of the previous universe and the metric of the next universe. And in the place where you match them, you need to introduce this conformal transformation to make the whole thing consistent. But as I said, I mean, I don't know. I haven't worked out the details, so I cannot.
So we are talking about one universe, and when it ends, to connect this to another universe, transformation.
Exactly.
Okay.
Exactly. The way I saw it is just that you try to justify physically a mathematical trick. So you need to go from the old universe to a new one. You need to match the two metrics. To do that, you need this conformal transformation, and you need to justify this physically. So, or not just to justify it physically, but this idea of a universe without time can justify it physically.
So does this imply that the particle, however the scalar field, this?
Yeah, it pops out. It pops out when you try to match the two metrics. Yeah.
Does it exist in both of the universes then?
No.
Just
I
in
think
the
it
second
exists
one.
in the second one. Yeah.
Okay, so does this mean like we accumulate with every? I mean, the idea was that there are several universes that we have to accumulate a scalar field per cycle.
I guess you could let this scalar field just decay during the universe, and in the end, it will just have transformed itself to this massless radiation, or it would have ceased from existence, something like that.
So I have a question or an idea. I don't know, maybe both. One of those rare moments. So this requires a couple. So this model, from what I understand, requires a coupling of the Einstein equations with a scalar field, right? Now there's a theorem that states that the coupling of scalar fields, more general P-form fields, is equivalent to the gravitational equations of with generalized with generalized gravity equations.
I mean, like Lovelock.
Something like that, yes.
You
For
could have
example,
minimal coupling.
Sorry?
You could have minimal coupling of the scalar field to the field equations. In that case,
Okay.
it goes. You can freely take it to the matter side, and
Could
okay.
what I'm asking is this: could we have this Penrose's model without requiring an extra scalar field, but instead require gravity to be more general than this? And what would that imply?
What do you mean, Costa? Is this are you trying to glue the unit? So are you asking about how to glue the different universes or eons?
So no. So what I'm saying is that Penrose's model, I don't know whether I'm right on this, but Penrose's model seems to require some kind of field, a scalar field to work. Okay.
To make this conformal transformation.
Yes. So what I'm asking is whether or not we can interpret this field as a correction to the to the equations of gravity,
so technically,
rather than a physical field.
When you say Penrose's model, you mean this conformal cyclic thing?
Yes.
I think this is related to this Will Curvature tensor vanishing at the beginning or near the Big Bang. So this association of initial low entropy.
I don't know. I'm just asking whether this could be, whether such a coupling is possible. I don't know. I'm just spitballing.
So the idea, I think, but I don't.
It's not exactly that you are adding a scalar field. I mean, what happens is that the metrics of the two universes need to be conformally related, and then this is like when you have scalar tensor theories that you have like two frames. You have the Einstein frame and you have the Jordan frame, and then you need to decide which is the physical metric. What is the metric with which you are going to then in the new universe to take measurements, right?
Oh, so you don't have a a single metric that evolves conformally. You have to.
You always have to.
The thing is, you have two different spacetimes. One that is well, you have many of them, right? Because in principle there are many cycles, but in
one
each cycle has its own metric, which in principle you are in general relativity. You are not in any other theory. And then the only thing is that when you are going to match in order to pass the information from one universe to the other, the conditions require that certain the metric need to be the metric of one era to the next one need to be conformally related. Okay.
What we're probably missing is that how is this scalar field related to the next universe? And I think Carlos gave me this idea to work with right now. In modified theories, you have two frames indeed. So there's a frame where your metric is Einstein, and you have a frame where your metric is not Einstein. It's the Jordan frame. And in this, probably you decide when you conformally related to metrics that your physical metric in the next universe is Einstein, right?
I am sure that there must be. I mean, the thing is, I am talking about something that I don't know very well. I mean, I'm sure there must be a criteria to decide which metric is the one that you need to use to measure physical distances, but I don't know what it is.
I mean, in modified theories, you almost always choose the Jordan frame to be physical. Maybe here you just violate that unofficial rule and say that my physical frame will be the Einstein frame, and the new universe will work with again with GR and not with some other theory. But I myself, the point is, I have seen a couple of papers with this theory, not anymore, and I'm not sure if they. It sounds correct to me right now that they're using the Einstein frame no matter what, but I've never seen them really going into that and how this, if there is a Jordan frame and I'm discarding it for some reason.
What about Cuba people? Do you have any question? Because we have silence on your side.
Preferably not related with conformal transformations.
Yes, yes, Nico, you wanted to talk about something, right?
Yeah, something entirely different from these things, actually. But
just a kind of yes, we merged, of course, the conversation with what we had before. But I don't know. Do you want to just hand wave your way through what you wanted to talk about?
I can try. Well, the idea, if there are no questions, first of all, if there are no...
I think we have had enough questions about this already, I think.
Okay. What I hope to talk about is the following one. When we speak, as I've told you, when we speak of cosmology and the two presentations you've already seen on cosmology, usually speak about this standard model and how this standard model fits our observations, etc. But this standard model is not the only possibility, and it's not the only possibility from many, many aspects. Why am I saying that it's not the only possibility? One reason is that, well, there are several, let's say, small inconsistencies, and one of them is exactly what happens in the early universe. We can't say anything about that if we stick to that model, at least. Something else is that we don't really know what happens in this late era of the universe with this accelerating expansion. And okay, the standard model takes that into account by introducing the very famous or infamous cosmological constant and saying that, okay, this will somehow emerge in the late times and will give me this accelerating expansion. But there are other possibilities within GR or outside GR that could probably explain, maybe even better or maybe differently, who knows, what we see. And okay, my presentation would be mostly how we mathematically treat these new versions or different versions of cosmology, and how can we decide whether one is good or is not good. And just to make a very, very long story a short one, we can, in principle, decompose Einstein's equations into simpler equations. You know, Einstein's equations that describe general relativity are very, very complex, very, very nonlinear. They're partial differential equations, and that makes them even more complex. And in general, it's very hard to say, I will try to solve them and get somewhere with them. It's even hard to analyze something and show that a solution you already know is stable or not. But speaking, for example, when we speak about cosmology, immediately we have some ideas that can simplify our space-time and simplify our gravity, or rather the curvature of this gravity, and somehow decompose these equations to very simple, to simpler ones. And so I can speak, for example, for an equation that would describe the evolution of the expansion parameter, the Hubble parameter of the universe, or a similar equation that could describe the evolution of the rotation of the universe, if I could assume that the universe has a rotation, or an equation that would describe the evolution of the sphere, so any deformation that the universe might have. And of course, I could have similar equations that would describe the evolution of matter fields, even they are scalar fields or standard matter, like dust, radiation, etc. And these equations can be analyzed because they are way simpler than the original ones. And what I hope to show you is that this way to analyze them is no different from how you analyze, for example, the dynamics of a pendulum. And what do I mean by that? You probably all have seen the model of a pendulum in Newtonian mechanics, so you know that it has two stationary solutions, let's say, to equilibria. One is on the bottom and one is on the top, okay? And the major analysis we conduct is to see what will happen close to the two equilibria. So if I have my system close to this equilibrium, what will happen? Probably it will go away, right? So this equilibrium can be deemed unstable. On the other hand, if I perturb it, if I take it very, very close to the other equilibrium, the bottom one, then this equilibrium is stable because this will oscillate and end up again to that. And the technique to analyze these equations is exactly the same. You have to locate such solutions that are stationary and so perturb them, apply this linear perturbation theory, let's say, around these solutions and check whether they are stable or not. And the funny thing you might come up from this is that solutions such as the standard model are not stable. There are cases where such solutions are not stable. So it's like the universe, if we believe the standard model, the universe that we live is the top equilibrium. So any small deviation from it would take us somewhere else. And that immediately brings up a question, whether we indeed live in such a universe. Is it viable to live in such a universe? Or do we live in a universe that is quite different and we have not observed correctly, if you want, this one? That's what I hope to say. And I don't know if hand waving helped in this case.
Yeah, I don't know. We had a long discussion with Jim. That was the in quotation marks problem, because it's been 3.5 hours now. People, how are you? Do you want to ask questions to Nikos?
Professor, you said the standard model is not only not the only possibility, and so how can we find out the different version of that?
Mm-hmm. Yeah. So you start by dropping the assumptions that the standard model has. For example, why should you consider the dark matter that you know nothing about it as dust? Because cold dark matter in the standard model means I interpret it as dust. It could be superfluid, or it could be something completely different. Immediately that takes you. Sorry, yeah. In a large scale, when you model the universe in the large scale, you need to make something to say something about the matter. And you say it's a perfect fluid, and you say that it's a perfect barotropic fluid. So your equation of state is the pressure is proportional to the density. Okay, and the simplest version of this proportionality is that pressure is zero. If your matter is cold, it's not relativistic. It's like ordinary matter. In the large scale, it will look like dust, so it will look like its pressure is zero. And this is an assumption that was made very, very early in cosmology. It was made by Einstein and de Sitter themselves when they started solving Einstein's equations with an idea of interpreting the universe as a whole. And they said that, okay, in the The matter that we know in the large scale, it will be behaving like dust. It will settle down like dust. So its pressure is very, very close to zero. The question is, now we know that this is not the only matter the universe has. How can you still stick to that assumption?
So
dropping this assumption immediately takes you away from the standard model, for example.
So matters may not behave like dust under pressure
In
is
the
not
large
zero.
scale, yeah. So the pressure, it could depend. Let's say the pressure could depend on the cube of the density, and that's superfluid. If you have indications from observation that dark matter could behave like a superfluid, you should take a new equation of state and resolve the equations. Another assumption you can drop, for example, is we admit that the universe is isotropic. Okay, we have a lot of evidence for that, but it's not necessarily conclusive. What would happen if the universe is not isotropic? There are solutions of Einstein's equations that accept an anisotropic universe, an anisotropic space-time. And I think there's work by Barrow and many others anyway, that show how these universes, these new models that are not isotropic, could isotropize in the long run. So after a lot of time, these universes would not be isotropic, but would look like isotropic. So you could be observing an anisotropic universe that has been isotropized. And that's again something that you can assume, or rather you can drop the assumption from the standard model and go somewhere completely different.
So universe may start from non-isotropic to isotropic, you mean?
Yeah, you should go back and resolve Einstein's equations for all these different versions by dropping assumptions from the standard model and see whether these models can be viable at first. Because if you prove that the Friedman model, the model that we use, the standard model, is unstable to an anisotropic perturbation, that means that your universe eventually would be anisotropic, right? If it's unstable to some matter perturbation that would lead to dark matter being superfluid, that means that we should interpret matter differently from standard model, go to a new model. That's the idea.
So resolve Einstein's equation, and the universe may not be isotropic.
Or homogeneous, if that matters. Whatever. There are solutions that are not isotropic and homogeneous, or just isotropic, or just homogeneous, or whatever.
There are different solutions.
Like hundreds, actually, yeah. Most of them are probably very good mathematical exercises, to be honest. So they're not necessarily physical solutions, let's say, or solutions that could apply to this universe. But some of them are, well, possible candidates for this universe as well. And it's a good idea whenever we hear, for example, that, okay, homogeneity is not so valid as an argument. We've seen recently that Planck data do not favor that, for example. What happens then? Should we change our standard model? And these all could provide an answer.
The standard model, I remember that Sterling Colgate used to say, do you know what is standard model? 1 gallon per flush. Because it's what you have in the toilets in the US, the American standard model. Anyway, I'm joking. Do you have more questions, people? Maybe Cuba? Ping, ping.
Nico?
Yeah,
Maybe you can highlight a bit about the Planck results that you just mentioned, because I'm sure.
Oh, you're speaking to the wrong person. But I remember that the latest results were not that conclusive as we initially thought.
No, what I mean is that like a bit more detail in what sense, so that people might get a context.
What Planck is and what we're trying to do with that. Okay, yeah.
Well, yeah, I guess Neil had given us a brief overview about it
Yeah.
with the CMB.
So
But-
you've heard about the CMB, the cosmic microwave background, right? This is, let's say, the first image we have of the universe, because if what we believe is correct, initially the light could not travel far. It was blocked somehow. It was engaged with this very hot, very dense matter. And the moment that light was allowed to travel for the first time freely, it gave us this picture. So it is the oldest picture of the universe we had. And it's because light escaped from matter practically from every point in the universe. You can still trace this today from every point in the universe and for every possible moment. And there have been many experiments, Planck is the last one so far, that try to analyze this radiation and see, well, several things. One of those is, for example, how well do we understand this standard cosmological model, let's say? So how sure are we that several of our assumptions are indeed correct? What more can I say about this? I'm probably very wrong to justify my my idea about the Planck experiment, but
more questions? I think people are kind of falling into lethargy, which is fine after almost 4 hours. So, Nico, is there anything else you want to tell us?
No, not really.
Okay. So, unless you have any other question, I would say we're going to close up for today. Tomorrow we'll have Monica Colby talking about astrophysical cosmology, if you want.